Welcome to the Concentrating Photovoltaics training. This training will focus on the recent technology of concentrating photovoltaics, or CPV, that can be seen as an evolution of the well-known photovoltaic, or PV technology. This training has been realized in the context of the European Solarize project that focuses on the adoption of solar energy in the 2Seas region. It is part of the training package emerging from the Solarize project that is pointing out some of the key topics on solar energy. We will start this training by giving some definition of relevance to concentrating photovoltaic system. Then we will focus on each of the main components of this technology and see the different options that are available for each of them. And we will finish the training by showing some examples of CPV systems before having a quick look at the strengths and weaknesses of this technology. Let's start with some definition about concentrating photovoltaics. First of all, what is concentrating photovoltaics or CPV technology? Well, the simplest answer is that this is a technology that associates a concentrator with a photovoltaic device. In a more detailed way, the concentrator is actually one or a series of optical devices that concentrate the sun beams onto a solar cell in order to increase the electrical output power of the photovoltaic device by increasing the intensity of input incident solar power. But then the question is, why using concentrating photovoltaics instead of only usual photovoltaics? Well, since CPV use optical devices to concentrate sunlight onto a solar cell, this allows for a reduction in the cell's area required for producing a given amount of power. Thus, the global aim of this technology is to significantly reduce the cost of electricity generated by replacing expensive cells area with less expensive optical material. This approach also provides the opportunity to use higher performance multi-junction cells that would be prohibitively expensive without concentration. As a result, CPV modules can easily exceed 30% energy conversion efficiency. They are even expected to exceed 50% in the medium term, when the common PV technology has maximum efficiency of about 25%. Therefore, CPV technology can be seen as an innovating and enhanced version of usual photovoltaics that would produce more electrical power output at lower cost. But before going a bit further into the details of this technology, it is important to have in mind what exactly is concentration. Concentration is the ability of a concentrator or an optic system to concentrate solar radiation. Then, in order to compare all the different concentrators, a concentration ratio has been defined as the quantity of solar radiation reaching the receiver compared to the quantity of solar radiation entering the aperture area of the concentrator. Thus, the higher the gap between these two values of solar flux, the higher the concentration ratio. From a more geometrical point of view, since the solar flux is a quantity of energy per unit area, the concentration ratio is also proportional to the difference between the aperture area collecting the solar radiation that should be maximized and the receiver area that should be minimized to get the greatest. Concentration ratio scale has been defined in order to classify into different categories the various CPV technologies in terms of their capacity to concentrate solar radiation onto a solar cell. It is start from the value 1, which corresponds to no concentration, up to several thousand as illustrated here. With this scale, we are then considering that low concentration technologies are between 1 and 10 sun. Medium concentration technologies are between 10 and 100 suns, which sometimes are also assimilated to low concentration. High concentration technologies are between 100 and 2000 suns, and ultra-high concentration technologies are above 2000 suns. Nevertheless, concentration presents several limitations, some of which are specified here. The first one is due to the solar resource itself, which is not a point source but presents an angular diameter, which limits the maximum concentration ratio to 46,000 suns. Other limitations exist that can be due to the nature of the solar radiation itself, the types of optics, and the geometry of the concentrator. For example, the maximum concentration ratio that can be reached for a 2D optics is around 216 suns because of the sun angle. To summarize, the concentration ratio is a key parameter for characterizing and classifying CPV technologies. However, it is not the only one. Indeed, if we are looking at classifying CPV technologies, there are several ways to do so. However, they all remain based on optics, but it can be in function of their geometry, the types of their primary or secondary optics, or about their tracking method. Nevertheless, the classification based on the concentration ratio remains the most usual and convenient. Now that we have seen some key definitions related to CPV system, we will focus on the main component of this technology, before looking at the different options that can be considered for each of them. From a global point of view, a CPV basic unit is composed of a solar cell, a concentrator that can be one or several optic devices, and a heat sink on the backside of the solar cell to regulate its temperature. Indeed, with concentration, the incident solar flux arriving on the solar cell is so high that it can raise its temperature and cause its deterioration. Then a heatsink is essential to firstly protect the solar cell, which is by the way the most expensive component of the system, and secondly to preserve its solar to electricity conversion performance that drops drastically when its temperature raised. As a matter of fact, an increase in solar cell temperature of approximately 1 degree Celsius causes an efficiency decrease of about 0.45%. The basic units of CPV are then connected together to form a panel. Then several panels are connected to form a module, and several modules are finally connected together to form a whole system that will be placed onto a tracking device, the last component of CPV's technology. Of course, several systems can be then placed on the ground and connected together to form a CPV farm, but this does not require new specific components. All the components required to transport, transform, or store electricity are then roughly the same than for the usual PV technology, and thus they will not be discussed in this training. So, as we have just listed the four main components of CPV technology, we will now give more details on each of them. So let's start with the most important component, which converts solar radiation into electricity, the solar cells. Depending on the types of CPV system, solar cells technologies are different. For low concentration CPV, where it is a question of increasing the efficiency at lower cost, conventional silicon cells are normally used, while the high and medium concentration uses multi-junction cells that are more efficient but also more expensive since they are more complex to manufacture and use rarer material than silicon. As for non-concentrated PV system, the cells used for low concentration are the conventional polycrystalline or monocrystalline silicon cells. Developed since the 70s, these solar cells are now a completely mature technology that are basically the cheapest way to produce electricity from solar resource. The cells have an efficiency only between 8 to 13% for amorphous silicon, between 10 and 14% for polycrystalline cells, or between 11 and 16% for monocrystalline. But the low concentration allows to increase the efficiency of the cells up to 20%. Nevertheless, using silicon as converting material for solar cells limits the amount of solar energy that can be converted into electricity. Indeed, as you can see on the diagram on the right, the gray area represents the energy arriving from the sun, and only the red part is converting into electricity. All the rest of the solar energy represented in gray is actually lost. Then other materials have been used in order to increase the solar to electricity conversion efficiency. It is in this context that during the 80s, multi-junction cells started to be developed. They are also called 3-5 multi-junction cells since they use elements from the column 3 and 5 on the periodic table. Starting with the 2-junction cell configuration, the 3-junction configuration developed in the 2000s can be considered today as a standard. The 4-junction configuration is an emerging technology. With the multi-junction configuration, these types of solar cells technology allows to better catch solar energy from different wavelengths, which makes them more efficient than conventional silicon solar cells. And their efficiency should even continue to increase as we add junctions, as shown by the theoretical models represented here on the diagram on the top right. Nevertheless, the development of these types of solar cells takes time, since there are lots of possible configurations of junction and elements, and these cells are more expensive than conventional silicon cells. As a matter of fact, 61% of CPV systems use silicon cells, while only 17% of CPV systems employ the 3-5 multi-junction ones. As a summary about solar cells, here is a comparative diagram from the National Renewable Energy Laboratory of the evolution from the 1975 to 2015 of different types of solar cells efficiency, whether they are multi-junction, thin film, or in silicon, and also whether they are used under concentration or not. And as you can see, multi-junction cells are the most performant, with efficiency between 26 and 44%, when crystalline silicon cells are between 20 and 27% only. Also, it is important to have in mind that emerging PV cells have for now an efficiency only between 7 to 14%, but they are based on innovative approaches that could overcome some of the inherent issues of the multi-junction cells. For instance, organic cells use elements that are much less scarce than multi-junction ones, which will decrease the environmental impacts of the production of solar cells and their cost. After having had an overview about solar cells, let's move now to the optics and the concentrators of CPV systems. Regarding the optics in CPV, there are actually two types of devices that are used. First, there are mirrors that are devices that reflect solar radiation, and secondly, there are lenses, which are devices where solar radiation passes through. These two types of optics differ in their geometry, where a large number of configurations is possible. We present here only the most common ones, from the simplest one like the flat reflector or the vitraf, to the more complex ones such as the Fresnel reflector or lens, the parabolic dish or the rod lens. They are all characterized by the following parameters: reflection, refraction, luminescence, concentration ratio, and acceptance angle. In CPV system, a single optical device can be used to concentrate solar radiation onto the solar cell, as shown here, or a combination of several optical devices can be created, resulting in a more complex concentrators, as it is shown on this slide, where there is once again several possible combinations. We present here three different examples of concentrators composed of 2 or 3 optical units. The first one is a double reflector concentrators, so-called the Cassegrain mirror, for which you have a picture on the bottom left, which is composed of a concave mirror as a primary concentrators and a convex mirror as a secondary concentrator. The second one is an association of Fresnel lens, for which you have a picture at the bottom center, with the rod lens, for which you have a picture at the bottom right. And the last one here is an association of 3 optics, composed of a Cassegrain mirror and the rod lens. Well, these are actually only 3 examples of existing CPV concentrators among many others that exist. But in order to compare them, their global performances have been based on 3 main characteristics. The optical efficiency, here in green, which is the ratio of the energy arriving on the concentrator aperture by the energy arriving on the solar cell. The acceptance angle, here in blue, that corresponds to the maximum angle at which incoming sunlight can be captured by the concentrator, and their irradiance uniformity, here in orange, that characterizes the quality of the outgoing irradiance from the concentrator and incoming on the solar cell. Then each CPV concentrator has its own advantages and disadvantages related to these parameters and are chosen depending on the application. Following the concentrators, we will now discuss an essential component that is especially required by the CPV technology, the heat sinks. One of the main problems of concentrating photovoltaics is the poor efficiency of the cells when the temperature rises. As a reminder, an increase of 1 degree Celsius of the solar cell temperature will drop its efficiency by around 0.45%. Then a heatsink is absolutely essential to firstly protect the most expensive component of the system, the solar cell, and secondly to preserve its solar to electricity conversion performance that drops drastically when its temperature raised. Then for CPV technology, 2 main methods of solar cell cooling are considered. Passive cooling that requires no energy consumption and which is based mainly on natural convection and for which heat cannot be recovered. And active cooling that requires energy consumption to make a cooling fluid circulate. Active cooling is based on forced convection and the heat can be recovered and used for a different application. Passive thermal dissipation cooling systems are mostly thermal radiators inspired by the form that already exists in the field of microelectronics for cooling microprocessors engraved on silicon wafers. They are less efficient than active cooling systems but are generally cheaper and easier to implement in the CPV system. They also require less maintenance. Active thermal dissipation cooling systems mostly use water or glycol water as heat transfer fluid, from which the thermal energy can be used for an air conditioning, hot water, heating, or desalination of seawater. They are more efficient than passive cooling systems, but are also more complex to implement and require more maintenance, which increases the cost of the CPV system. We will finish this section with the last components, the tracking systems. There are two main types of tracking systems. The single-axis tracker, where the panel rotates around one axis, generally in an azimuthal shift from east to west over the course of a day. And the dual-axis tracker, where the panel rotates along an east-west axis and along a vertical axis. Within the single-axis tracker category, there are two further types. The active trackers that consume energy since they use motors, gears, or hydraulics to move the module. And the passive trackers that do not consume energy but use a specific device that contains a compressed fluid with a low boiling point, which evaporates into a gas when heated up by the sun, that adjusts the equilibrium of the CPV system. Nevertheless, these passive trackers are less accurate than systems focused on light detection technologies, and they require manual intervention to optimize the north-south direction depending on the season, as they are not designed to be dual-axis. However, compared to module fixed at an optimal angle, a single-axis tracker typically increases electricity production by 27% to 32%, and a dual-axis tracker by 35% to 40%. Considering the economics, the choice of which tracker to use is largely a decision involving the additional investment and maintenance cost over time versus the increase in energy and financial output delivered by the system. In order to have a better idea about the difference between the two categories of trackers, here is a table that summarizes some of their advantages and disadvantages. Above the fact that a dual-axis tracker will increase more the solar efficiency of the CPV system than a single-axis trackers, it is also important to point out that a single-axis will require simpler equipment and that the manufacturers of single-axis equipment claim that the additional benefits of the net energy output provided by the dual-axis system over a single-axis system is often lost through the additional cost of its installation and its associated maintenance. Also, dual-axis systems have more moving parts than single-axis trackers. Their design is more complex with the use of additional motors and sensors to track the sun. This increases the risk of malfunction and failures. In addition, single-axis trackers tend to have a lower profile, sometimes half the height of dual-axis trackers, and are therefore more likely to receive building permits. Finally, the dual-axis tracker can have also the disadvantage of pointing up into the sky on a cloudy day, whereas single-axis trackers, thanks to their tracking model, will be where they should be. The single-axis tracking model therefore eliminates unnecessary tracking movement that cause additional wear, tears, and power loss. The commercial opportunities represented by the single-axis tracking technology are thus more present on the market. Now that we have finished with the main components of CPV technology and their different options, we will take a look at some examples of CPV systems. Here we present images of Fresnel lenses CPV systems on the right and a parabolic mirror CPV system on the left. To finish with this training, we will have a look at the key points of the CPV technology, including technical and industrial aspects. We summarize in this table the strengths and weaknesses of CPV technology, considering technical and industrial aspects. The main advantage of CPV is its high efficiency compared to PV and its possible additional waste heat recovery when using active cooling. In addition, CPV also increases and stabilizes the energy production throughout the day due to tracking. Nevertheless, concentration implies harnessing only the direct solar radiation part, even if there is some research about harnessing also the diffuse radiation part, and the addition of optics implies additional optical losses, a sufficient and reliable tracking as a frequent cleaning. Although research on cells, modules, and systems for CPV has been ongoing for decades, CPV only entered the market in the mid-2000s. With a total of more than 300 megawatts of power, it is still a young and small player in the market for solar electricity generation compared to conventional flat-plate PV. This implies a lack of reliable data for markets, prices, and technology standardization for industry. However, the current trend in the CPV industry is more about the development of lower-cost products with a much lower solar concentration to benefit of a quite low capex and which enable fast growth instead of high-concentration PV that requires a high initial investment. Taking advantage of being modular from the kilowatt to the gigawatt scale now, the concentrating photovoltaic sector is also less sensitive to variation in semiconductor prices, which implies interesting economic prospects. Thus, even if this sector still lacks sufficient development inducing economic, technical, or industrial gaps, it is essentially due to the novelty of this technology. But its development is constantly increasing, and with time, the difficulties of market entry regarding the competition with PV, the bankability, and the perception issues are going to fade away, given the greater potential for efficiency increase of this technology compared to PV. If you are interested in more information about CPV technology, such as its key facts, or to read a more comprehensive overview of its market and industry, its perspective and its research and development, I advise you to take a look at this report from Fraunhofer Institute for Solar Energy Systems and the National Renewable Energy Laboratory that you can download for free using the given links. Thank you for your attention.